Mhm.
I've done some shopping there, but that's about it.
He was on the first U.S. Everest expedition,
Huh.
75.
Wow.
Oh, we have lights.
Lights. We have everything's about ready to go here. And we have some audience here. Don Nab's on. I don't know if Barbara Harris is watching in the background there. I gave her a heads up. Andrew Corkhill's on. It's nice. Andrew is a longtime league supporter. Did a lot of their observing programs.
Scott, I don't know why, but you're really, really low for me to hear.
How about
It
that?
might just.
How's
Oh,
that?
wow, there you are. Yeah, I can
Is
hear
that
that.
better?
Much
Yeah,
better.
much.
I'll put my voice right next to the microphone. How's that? So
You do that.
okay.
Yay to go, Scott.
Nah. That's right.
Now and then, an obscure star briefly flares up, brightening up to 1,000,000 times. It's an event called a nova. The star V906 Carinae erupted as a nova in 2018. Observations from 3 satellites provide new insights into what happened. NASA's Fermi mission has seen 14 novae since 2010. Before then, astronomers didn't think novae could glow in gamma rays, the highest energy light. When a white dwarf pulls material from a companion star, the gas forms a thickening layer that eventually erupts in a thermonuclear fireball. A nova is born. Led by a team from Michigan State University, astronomers studied V906 Carinae using high-energy data from Fermi, NASA's New Star X-ray telescope, and invisible light from a Canadian satellite named Bright Toronto. Shaped by the orbital motion of the stars, the explosion debris first forms a thick, expanding ring around the system. Then, after 10 days or so, fast outflows, likely driven by residual fusion on the white dwarf, strike the ring. The resulting shockwaves produce gamma ray and optical flares that radiate away most of the nova's energy. These observations provide the first direct evidence that shockwaves can power most of a stellar explosion's visible light. Figuring out how they work in nearby novae will help us understand more powerful events much deeper in the cosmos.
Well, hello everyone. This is Scott Roberts from Explore Scientific and the Explore Alliance, and I've got Terry Mann with me here, and she is hosting the 36th Astronomical League live program. And it's been a real pleasure to do these with you, Terry. I think it's very inspired that 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 you and the executive staff do so much to reach out to the 20,000 plus members that you have within the Astronomical League. I will turn this over to you, but know that I'm one of your biggest fans. So
Thank you, Scott. Right back at you. We really appreciate everything that you have done too, Scott. You've always been there, and we greatly appreciate that.
right back
And
there
also,
at you too.
yeah, we've got more stuff going on this year with the league that Carol will fill us in on. And we've got Chuck Allen that will give the talk tonight. We're looking forward to that. And David, I'm still used to calling you David. David, we will start with you, and thank you. You have really been here every time that we have been on. And I am so grateful for the time it takes and the energy that you give to us just to do this. So thank you so much.
Well, thank you, Terry. I am today, I really was enjoying the NASA program that was put on at the beginning just now. And because it might have something that's pretty current. It's something that I really found out about while I was reading Starlight Nights for the first time by Leslie Peltier back in 1965 for the first time. I think I've read it about 99 other times. I love that book. But anyway, Leslie was talking about one of his favorite variable stars named T Corona Borealis. And he said that in 1866, it became a nova. And then they were able to find that other times earlier in history, it became that star also was a nova. And so they were suspecting that it may be a recurring nova every now and then. And so Leslie decided to watch it every single night. And then in February of 1946, the alarm went off and Leslie got out of bed and he thought, oh, I don't really feel like it this morning. So he went back to sleep. That was the night the T Corona Borealis rose out of its bed, stood up, and brightened up, and from 10th magnitude to about 3rd magnitude in a few hours. And where was Leslie Peltier? He said, I was asleep. And he says at the end, he said, I still look at the field of T Corona Borealis every night, but it's no longer in friendship. We're not close anymore. And I loved reading that, how he sees that the stars are his friends like his children. And I feel the same way. For my quotation today, I want to quote from a John Dryden poem that he wrote in 1667. It's called Annus Mirabilis. And the first line is, to see this fleet upon the ocean move. Well, what is the fleet he's talking about? It's a fleet of clipper ships. And I know that I'm going to get thrown off for saying this, but this might have something to do with the password that some of you had to use to get into our meeting today. Also might have something to do with the dog that I grew up with when I was a teenager. That dog was named Clipper. And he was a beagle, and I loved that dog, and I miss him terribly. And he was really quite the wonderful dog to have around, especially on the night of December 17th, 1965, when I took out my telescope and started to search for comets. That was going on to almost over 60 years ago now. I'm still searching. I don't expect to ever find another one, but I love the search. Anyway, let me quote from John Dryden's 1667 poem, Annus Mirabilis. To see this fleet upon the ocean move, angels drew wide the curtains of the skies, and heaven as if there wanted lights above, for tapers made to glaring comets rise. Whether they unctuous exhalations are, fired by the sun or seeming so alone, or reach some remote and slippery star, which loses footing when to mortals shown, or one that bright companion of the sun, whose glorious aspect sealed a newborn king, and now a round of greater years began. Now influence from his walks of life did bring. Have you not seen when whistled from the fist, some falcon stoops at what her eye designed, and with her eagerness the quarry missed, straight flies at check and clips it down the wind. Thank you very much. And Terry, it's back to you.
Thank you, David. You know, I'm sitting here listening to that, and I don't know why, but when they talked about the ocean and the sunset, I thought of the Winter Star Party. I think because everybody that was there, I've seen beautiful pictures of sunsets. Oh, and I know that has nothing to do with what you wrote or what you read, but that is one of the first things, and it just made me think I could visualize the ocean. You know, it sounded so pretty. Thank you so much, David. And again, thank you for your time.
Thank you. And I think that Dryden himself would have agreed with what you just said. That's a good interpretation.
It's funny. Certain things just make you jump to different memories that you have. And the Winter Star Party down in the Keys is definitely one of the good ones. So thanks again. All right. Carol, how about if we go to you and you can kind of update us on what's going on with the league or anything else you want to update us on?
Sounds good. And David, thank you for those wonderful words. It's always such a pleasure to hear from you. Thank you, Scott, for being there for us all the time for the league. And Terry, thank you for heading this up each month.
Thank you.
Yeah, we have a few updates from Alcon, the National Convention of the Astronomical League. I'm going to share my screen and talk about that just a little bit. Okay, one thing that has just gone online is the actual sign up for rooms. And if you have your cell phone tonight, you're seeing this, check out the QR code and that will take you directly to room reservations for the Doubletree Hotel in Overland Park, Kansas, a suburb of Kansas City, just a few blocks from the Missouri Sun. So we've got the great rates of $139 per night, very affordable, and we would love to have you attend. If you'll notice on the last line there, it says the default is 6 nights. So all you do is change that to whatever amount of nights you want to stay. And we're already getting several room reservations in, and we're very thankful for that. And we hope to see you then. I'll just go over briefly again the speaker list, which is in the top half of the listing here. Our keynote speaker will be Stefan Alexander. He's a theoretical physicist, cosmologist, jazz musician, and author of The Jazz of Physics. And since Kansas City is the home of jazz, he's going to participate with the band we're going to have at the banquet. So that should be a real thrill. Also, there's a person named David Levy who's going to be at the convention as well, I believe. Right, David?
Yes, I am going to be there, and I would like to say a few words.
Sure, go ahead.
And one thing I forgot to say, I was telling the story about the poem and then talking about the Nova the Nova movie we saw, and I was telling the story about T. Corona Borealis and told her that lovely story about Leslie Peltier. But what I didn't say is that the star has been acting really funny. Last night it was the faintest I've ever seen it at 10.3. And it is supposed to rise again to about third magnitude sometime between now, tonight, and the year 2026, which would be 80 years since the last one and 160 years since the 1866 one. And so we're really looking forward to that. And I think that now as we go back to the Astronomical League, I'm really looking forward to being at that convention this summer. Carol, back to you.
Well, we're looking forward to having you. Many of you probably know, but David's papers are there at Linda Hall Library, as well as his first telescope ever. So that's going to be a real thrill. Another speaker we're going to have is Kevin Stenson, professor of physics from Vanderbilt. And finally, one of the main speakers is going to be Tim Russ, actor, musician, screenwriter, director, and amateur astronomer. Some of you Star Trek fans will remember him from those days. And he's also a jazz musician, so we're going to have a lot of fun with the jazz band and our various guests together. So that's where we are right now. We've talked a little bit about the events of the convention. First of all, the first night we will have a visit to Gottlieb Planetarium at Kansas City's Union Station. And as I said just a few minutes ago, David will hold forward at Linda Hall on the second night of the convention. We have the proverbial Starbecue at the Overland Park Arboretum, and Powell Observatory is also on the books for Friday night as well. And finally, the awards banquet on Saturday night. We've also got two sponsors already. Of course, Explore Scientific, which Scott's always been very generous in that respect. Daystar Filters, and many more will be coming online. And I think that's it for right now, Terry. And now back to you.
Thanks, Carol. I can vouch for how easy it is to make reservations. I've already got mine in, and it is. It's very simple, and the rooms look really nice. So I'm looking forward to it. It'll be nice to have a jazz band. Will they be at the banquet? Was that where they'll be playing? Or
Yes, they will.
that will be nice to be able to just sit back, listen to some music, and kind of talk to everybody for a little while. So that'll be great. I'm looking forward to it. So, all right. How about let's go. Thank you, Carol. Appreciate that. And we'll go on to Chuck Allen. He's going to be our speaker tonight. And Chuck is the vice president right now of the Astronomical League. And we've all kind of known him, and he's known all of us for quite a long time. So there was just a tiny bit of a change in the subject that Chuck's going to be talking about. Instead, he will be talking about the Andromeda galaxy. Am I right, Chuck?
Correct.
Okay. So welcome. I'm glad to see you here. It's been a while. So, all right. Let me tell you a little bit more about Chuck Allen. As I said, he's the vice president of the League and a past president of the League. He founded the National Young Astronomer Award in 1991. He has received in 1998 the G.R. Wright Service Award. He holds the League's Master Outreach Award for nearly 600 public programs logged, and is a gold level member, Master Observer with 43 programs completed. Oh my gosh. Wow. You know everything. Chuck coordinates 3 observing programs and co-chaired Alcon 21 virtual during COVID. He's a past president of the Louisville Astronomical Society and current program director for the Evansville Astronomical Society. From 1995 to 2002, he was a lead judge at Intel, which is now Regeneration. There we go. The International Science and Engineering Fairs. So, Chuck, thank you for being here. I look forward to your talk, and I will let you explain your talk.
I appreciate it, Terry. Thanks. It's always good to be here among friends I've known for so many years. Carol and Terry and David I've known for at least 2 decades, maybe 3. And Scott was the first person to step forward and give the support we needed to get the National Young Astronomer Award program off and rolling. And it's now in its 32nd year, thanks to all of his support. So thank you so much. If you saw an announcement earlier that I was going to be speaking on a topic relating to distance, I had to change that. I changed it a long time ago and forgot to tell Terry about it, so I apologize. But I've been giving that talk so often, I thought I would do a little change up here. So what we're going to be talking about now is something much more familiar, perhaps, to even beginning astronomers as well as experienced ones, the Andromeda galaxy. And let me share screen here. And we'll go to this and start the slideshow. Okay. Those of you who are even starting out, if you know where to look in the sky, find the great square of Pegasus, follow two pairs of stars in Andromeda up to here, and they point right to a fuzzy patch in the sky. It's an oval patch. And it's one of perhaps as many as 2 trillion such patches that we now know exist in our universe. This particular fuzzy patch, the Andromeda galaxy as we now know it, is unique in one respect. There's no galaxy that ever created a greater mystery for longer than this little object, or unlocked more secrets about the nature of the universe. And I think it's very important to see how confusing it was and for how long and what biases the study of the Andromeda galaxy ultimately overcame. The first person ever to record in history an observation of Andromeda was Abd al-Rahman al-Sufi, a Persian astronomer, in a book of fixed stars that he wrote in 964. This was the first known record of anyone observing this patch in the sky, although unquestionably it had been observed for centuries before that in the dark skies of Australia, Africa, South America, North America, or wherever. He described it in his book as a small cloud. And the interesting thing about it was that the small cloud never moved. It was always there. It was many, many years later, in 1612, that Simon Marius came along and applied a telescope, which was a brand new invention in the world. We had only had telescopes for about 4 years, and he aimed a telescope at it, a small one, of course, a refractor, and recorded that he had seen a dull, pale blue light, which increased in brightness toward the center like a candle shining through horn. And anyone who's observed Andromeda through a small telescope would completely understand this description. It's quite apt and is indeed what it looks like. In 1745, the first good guess as to the nature of Andromeda came down the pike. It was from a French astronomer named Pierre-Louis Maupertuis. And in 1745, he opined that these nebula-like objects, Andromeda, are in fact collections of stars, although no one could prove that. And he was first to use the term island universe. And it's very important to understand that in that era, the stars we see in the sky were thought to be part of a singular island universe of stars, nebulae, and so forth. And that these oval nebulae, these spiral nebulae, as they came to be known, were simply within this one island universe of our own, and were therefore close by. Charles Messier, and this is a name that all beginning astronomers get to know very early because he recorded a wonderful list of deep sky objects that are the primary targets of all astronomers when they start out and later in life. And object number 31 on his list was this Andromeda Nebula, this big oval nebula, the small cloud that had been recorded in Al-Sufi's book. Now, he erroneously attributed the discovery to Simon Marius, saying that Marius was the first to record it in 1612. And you can even see that recorded on Messier's excellent drawing of Andromeda, along with 2 of its companion objects. The interesting thing about this is that, of course, Marius was not actually the discoverer. We just don't know of anyone who had seen it beforehand. Messier did his work from the top of the parapet you see here at the Musée de Cluny in Paris. There's a little porch right at the top, and he sat up there in days long before light pollution and started recording all of these objects that he would see in the sky, clusters and nebulae of all kinds, with a view toward preventing them from confusing his search for comets. That's what he wanted to do, find comets. And interestingly, he became famous not for comets, but for the list of confusing objects that he found. And interestingly, Edmund Halley wanted to catalog deep sky objects and stumbled on a comet that he became famous for. So they each became famous for something that they were not looking for. Most of you have probably heard of Immanuel Kant, a great German philosopher. He's often considered the father of modern philosophy. And wow, did he come up with a fantastic guess as to the nature of Andromeda. Just read this. This is in 1775. It is far more natural to regard the spiral nebulae as systems of many stars whose distance presents them in such a narrow space that the light reaches in a uniform pale glimmer. Their shape, the feebleness of their light, which demands a presupposed infinite distance, all of this is in perfect harmony with the view that these elliptical figures are just universes and, so to speak, Milky Ways. That's from a philosopher, not an astronomer, and he got it absolutely right, although he was basically ignored. And he was ignored because of a bias that existed. The bias was that our Milky Way, our island universe, was the only one, that we were the center of the universe, that our giant mess of stars existed in a giant void, that the universe was static, extended forever in the past and in the future. And this bias was so strong that even in the 1900s, Albert Einstein, when he came up with this great theory of general relativity, included in it a cosmological constant to make sure that the universe came out as being static, which we know it's not. William Herschel, as you grow into astronomy, you'll start tackling perhaps many objects on the Herschel list. We have many of these programs in the Astronomical League, the Herschel 400, the Herschel 2, each contain 400 of his objects, most of which are galaxies. He cataloged 2,400 of them. And he charted, actually made a drawing of what he believed our island universe looked like. And he believed, as all the astronomers before him, that these spiral nebulae were objects within this island universe, perhaps new solar systems forming in a sort of a disc-shaped, spinning, whirling disk of gas. Now, William Parsons, the third Earl of Rosse, a British astronomer, built a giant telescope in Ireland called the Leviathan of Parsonstown, and used it to actually start sketching some of these spiral nebulae. And here's one he made of M51, and you can see that he wasn't far off from actual photographs that we have today of it. And he was the first to sketch the spiral structure of Andromeda as well. So all of this came forward to about 1864 when William Huggins, a British astronomer, took a spectrum of the spiral nebula Andromeda, and he announced that it was not what he expected to find. The spectrum he got from it was not that he was getting from other great emission nebulae, like the Orion Nebula, for example, but it was more akin to the spectrums of stars. So this was the first clue that something was up, that maybe Andromeda was not a spinning disk of gas within our own universe. A second clue came along in 1885. A bright star erupted in the Andromeda Nebula, and it outshone the entire galaxy. It was called S Andromedae, or Nova, 1885. Scott was very helpful in showing us what a nova is at the beginning, and that's what people thought this was. It was a nova that was appearing in a spiral nebula within our one island universe, our Milky Way. And if it were a nova, it would have been about the right brightness. No one knew that it wasn't a nova at all, but actually a much brighter supernova that was occurring in a galaxy far away from us. It rose to magnitude 5.85, so it would have been visible to the unaided eye. And it's rather surprising that it's the only supernova we've ever observed in Andromeda. It's surprising because recent studies of the amount of aluminum-26 in the universe suggest very accurately that the number of supernovas we expect to occur in spiral galaxies like the Milky Way or Andromeda is roughly 2 per century, but we still have only the one in 1885. Well, photography came along, and a little after Christmas in 1888, Isaac Roberts took the first photograph of Andromeda. And here you can see its spiral structure. And about that same time, an astronomer in the United States named Vesto Slipher Lowell Observatory. And he's famous, of course, for many things, including hiring Clyde Tombaugh, who a year later discovered Pluto. But Besto Slipher was a brilliant man, and he discovered through spectra the recessional velocities of spiral nebulae using spectrum redshifts. But he found of the 25 spiral nebulae that he observed, 3 of them were approaching us, and the other 22 seemed to be receding. He attributed some of this to the sun's movement in the Milky Way, not realizing anything that he was stumbling upon, which was actually the first evidence of the fact that the universe was expanding. M31 he found, that is the Andromeda Nebula, he found to be approaching us at about 300 kilometers per second. Meanwhile, 3 major developments were unfolding in the world. The first of those came at the hands of Henrietta Swan Leavitt, one of the most brilliant astronomers ever to live. It's a shame that bias probably prevented her from receiving a Nobel Prize that she richly deserved for the discovery she made in 1912. She was studying under Edward Pickering at Harvard College Observatory. She was studying variable stars and cataloging them. At that time, we were doing parallax studies on the distances to these closer stars, and she was noting the periods of these particular Cepheid variables, and they came in different varieties. Some had short periods, some had longer periods, where they would brighten and dim at regular intervals. And what she noticed, and I'll just try to give you an example here. Let's suppose she noticed this star right here had a period of 2 days. So she would plot it here. And she knew that from parallax that it lay at a distance of 32 light years. Now, 32 light years, the reason I picked that for this chart is 32 light years is the distance at which we judge an object's absolute magnitude. In other words, if you take a street light and say, how bright would it look at 1 mile? And then you compare it with all other different kinds of lamps and lights and how bright they would look if they were all at 1 mile. Well, 32 light years, or 1 parsec, is the distance that astronomers have picked for that purpose. 10 parsecs, excuse me. So how bright would this star be? Well, it is at 32 light years. It is at 10 parsecs. And it had a visual magnitude of +3, so she knew it had an absolute magnitude of +3 because it was already at that standard 10 parsec distance. Well, then a second star was noted that had a period of 2 days. Only we knew from parallax studies that it was 320 light years away, and it had a visual magnitude that was 100 times fainter than the first star. Well, if it's 100 times fainter, under the inverse square law, we know that it has to be 10 times further. So it was 320 light years. It was 10 times further, so it had to be 100 times fainter. And so if it had been moved, if you had moved that second star forward to 32 light years, it too would appear at magnitude +3. 2 more stars. These stars had, let's say, 4-day cycles, Cepheid variables. I'm making up these numbers just for the purpose of the chart. But suppose she found a star that was a Cepheid variable that had a 4-day period, and it was at 32 light years. It had an apparent magnitude of 0, and therefore it had an absolute magnitude of 0. But then she would observe a second 4-day Cepheid that she knew was 320 light years away, that shined at +5 absolute magnitude, 100 times fainter. 100 times fainter. What if we moved it forward 10 times closer to 32 light years? It would be at magnitude 0 as well. What she was determining was that there was a relationship between the periods of these Cepheid variables and how bright they were absolutely, how bright they would look at 10 parsecs distance. That made them standard candles. So, for example, let's suppose you saw the star marked in yellow here, and you knew it had a period of 4 days. Okay, and it's coming in at magnitude +15. Well, you know that other Cepheid variables with 4-day periods at the standard distance of 32 light years had absolute magnitudes of 0. But this one was 1,000,000 times fainter in apparent magnitude. 1,000,000 times fainter means, of course, that it has to be 1,000 times further. So she would be able to calculate that the distance to that star was 32,000 light years. This was revolutionary. She was finding Cepheid variables at great distances beyond our ability to determine parallax in the Milky Way and even in the Magellanic Clouds. And from this was able to extrapolate the distance to these to these objects at great distances. About the same time, a second development was occurring, the installation of the 100-inch Hooker telescope at Mount Wilson Observatory. This would prove to be a tremendous advantage to astronomers observing these spiral nebulae. And what occurred next, of course, was a debate, a great debate that was held at the Smithsonian Institute in April of 1920 between Carlos Shapley and Abel Curtis. These were both American astronomers, and they were brought together to debate the nature of the spiral nebulae. Now, Carlos Shapley argued that the spiral nebulae were within our Milky Way galaxy. He based this on one erroneous study by another astronomer named von Manen, who concluded that he had observed over a period of years rotation in the galaxy Messier 101. Well, of course, over a period of just a few years to observe rotation in a galaxy would mean that the galaxy was rotating at vastly greater than the speed of light at the periphery, and that's impossible. However, if it was simply a spiral nebula in the Milky Way, perhaps, yes, you could observe its rotation. So he used that as evidence. Unfortunately, it was bad evidence. He also noted that a nova, which is what he thought the event in 1885 was, cannot possibly outshine an entire galaxy at a great distance. Again, not realizing that that nova was actually a supernova. Curtis, on the other hand, argued that he had observed 11 regular novae that behaved like the novas you saw in the film at the beginning of this program, that he had observed 11 of them in the spiral nebula of Andromeda. And that's far too many and far too small an area of sky to be consistent with just the random occurrence of novae in this island universe of ours. He also noted dark lanes that were appearing in photographs of Andromeda that were consistent with dark lanes we see in the Milky Way itself as we look up in the summer sky. And shortly after this, a man by the name of Ernst Oppik, an Estonian astronomer, was able to correlate the rotational velocity of stars in M31 to the mass of the galaxy and to calculate the distance to the spiral nebula, in his estimation, at 1.5 million light years. This was vastly further than any estimate before and totally inconsistent, of course, with something in the Milky Way itself. Well, all of these developments came together in the work of Edwin Hubble in 1924. And it was Edwin Hubble using that 100-inch and using the knowledge we had from Henrietta Swan Leavitt about the relationship between Cepheid variable brightness and distance that allowed him to determine the distance to this spiral nebula. He discovered on November 23rd, 1924, that's a date, the 100th anniversary of which is coming up in just a matter of months. He was able to find a Cepheid variable in Andromeda. And using the period luminosity relationship discovered by Henrietta Swan Leavitt, he was able to determine that Andromeda is in fact a pinwheel of stars that lies at least 750,000 light years from the Milky Way and is itself an island universe. He published this in the New York Times. On January 1st of 1925, he mentioned it at an AS meeting, but it did not appear in a peer-reviewed scientific journal until 1929. Such was the force of this static, Milky Way-centered, everlasting universe that had just stultified all advances in astronomy to that time. Eventually, though, Hubble became known for this work. Further studies were done that confirmed his work. And Hubble went on to correlate Vesto Slipher's study of the recessional velocities of galaxies to the distances that Hubble was determining using the Cepheid variables. As a result, he was able to determine that, in fact, the universe is not static, it's expanding. He overestimated the rate at which it was expanding, but he was the first to discover that. The debate was over. The Milky Way was one of countless island universes in an expanding universe. The galaxy itself, Andromeda, is 152,000 light years wide and contains probably around 1 trillion stars. It seems to be the king of the local group. Or is it? In February 15th of 2024, that's just a couple weeks ago, the International Society for Radio Astronomy Research published some notes in the Proceedings of the Royal Astronomical Society, concluding that both Andromeda and the Milky Way have masses roughly equal to 800 billion solar masses, in which case we may be underestimating our own size compared to Andromeda. Much as a fighter will always see the opposing fighter across the ring is probably bigger than himself or herself. Andromeda has older, more red stars, but it is very luminous and is in fact the fifth furthest permanent naked eye object that we can see in the sky. Naked eye observers have been able to see objects as far away as 13 million light years. That would be the improperly labeled here M5128. It's actually NGC 5128 or Centaurus A, which lies at about 13 million light years. That object has been seen in very dark skies and would be quite a bit further than Andromeda. Despite its having more older, redder stars, both Andromeda and the Milky Way are considered to be what are called Green Valley galaxies. They both lie in this valley between having an excessive number of blue hot stars or older red stars and lie in sort of a medium luminosity region among galaxies. So both spirals are pretty normal. In studies done in 2003 involving new determinations of Cepheid variable distance, and in 2004 measuring infrared surface brightness of galaxies, and in 2005 looking at eclipsing binaries, we've pretty much concluded that the distance to Andromeda is about 2.54 million light years. That's about 15 quintillion miles for those who like to use that. If you could see the full extent of Andromeda with your unaided eye, it would look larger than a full moon. Well, the extent of the galaxy in the sky is over 3 degrees, and it's the largest M object in the sky for that reason, and the fourth brightest behind the Pleiades, Messier 24, and Messier 7. The core of the galaxy is rather interesting. As you delve into the core, you begin to see that the core appears to have two centers. A bright center seen here called P1 and a dimmer center seen here. And if you apply HST to this and look more deeply, you'll find that that large bright center lies here, consisting of red stars, older stars. And the second center lies close to a black hole at the center of the galaxy here. And these stars are hot, young, and blue stars near the center. These blue stars, when they reach their aphelion point from the black hole, kind of stall because they're moving more slowly in their orbits and have been imaged dancing at the aphelion point around the black hole. It's rather interesting. Andromeda's black hole is about equivalent to 140 million solar masses. That's more than 32 times the mass of the black hole at the center of the Milky Way. Now, interestingly, in 2006, the black hole, which lies where my cursor is right here, brightened considerably. It brightened, in fact, 10 times and can be seen right here. And then it brightened a little, it started to fade rather, and today is still noticeably brighter than it was before this initial brightening. What it's thought is occurring is that the black hole is devouring one or more stars and brightened as a result of radiation being emitted from the accretion disk around the black hole. Globular clusters abound in Andromeda. It has 460 known globular clusters compared to 150 in the Milky Way. And this might be a good indication that, yeah, Andromeda may be more massive than the Milky Way after all. G1, or Mayall 2, as it's seen here, is the largest globular cluster in the local group of the galaxies. It's twice as big as the great Omega Centauri cluster in our own galaxy. And indeed, this globular has a black hole in its center, 20,000 solar mass black hole. So it's thought that what this actually is the core of a galaxy whose outer remnants were stripped away when it passed through the Andromeda galaxy. Another globular star cluster in Andromeda called G78 is the most massive globular known. And it too has a black hole at its center with a mass of 100,000 solar masses. Lots of black holes abound in Andromeda, it seems. In Andromeda, we've also discovered a new class of globular clusters. These are globulars that tend to be larger than 100 light years in diameter and less dense than the ones that we observe around our own Milky Way. Now, really interestingly, in 2009, we observed a micro-lensing event. We observed a star passing in front of another star. And as a result, the foreground star caused a magnification of the star behind it, seen in the peak here. But as it was passing and starting to dim again, there was a little secondary microlensing event consistent with a planet orbiting the foreground star, also lensing the star behind it. This is the first discovery of a planet in another galaxy. It's called PA99N2 and is estimated to have a mass of approximately 6 times that of Jupiter. The galaxy itself is rather warped, as you can see in this image. The cause of the warp is not fully understood. It could be caused by the third major member of our local group of galaxies seen in the lower left, which is M33, or the Triangulum galaxy. It lies only 750,000 light years from Andromeda, considerably closer than we do. Or it may be caused by those two companion galaxies that you always see in the pictures of Andromeda, M32 on the left and M110 on the right. So here is M32. That's the first of the major companions I want to talk about. Apparently, this object can be thought of as another galaxy that was absorbed by passing through Andromeda, and the core of the galaxy got spit out like a peach seed. Most of the stars from this former galaxy are now in Andromeda's halo, and M32 also has a black hole in its center, estimated to be as large as potentially 5 million solar masses. It has about 3 billion stars in it and is about 7,000 light years in diameter. The other major companion to Andromeda is M110, Messier Object 110. It has about 10 billion stars and is about 17,000 light years long. And its core stars are very hot. They're hot because they're burning helium in their cores at this point, but it has no black hole in its center. There are 38, if you can believe it, 38 other companion galaxies to Andromeda, a total of 40, and they span 6 constellations: Andromeda, Pegasus, Cassiopeia, Triangulum, Perseus, and Pisces. And 9 of them lie in a plane that runs through the core of Andromeda, suggesting that they had some sort of common origin. And of course, we know that Andromeda is fated to collide with our own galaxy. And here are the paths that are estimated to take. You see Andromeda moving over the top in the red line, the Milky Way moving toward it. They'll loop around each other and collide at the center. Meanwhile, M33, the Triangulum galaxy, will have a front row seat as it whips around the pair as they begin to merge. This is a video showing what will happen. Watch how that little Triangulum galaxy just watches from the cheap seats.
Yeah.
Here they loop around.
Uh-oh. Oh. Oh.
And form an elliptical galaxy.
Wow.
Notice also how stars are flung off into the universe. Many will depart the scene completely and probably reform into irregular or dwarf galaxies. M33, that little galaxy in the upper right, will also be absorbed at some point. So what will we see here? Well, the first thing we would see here, if we were around to see it, this is what we see now, little Andromeda up next to the Milky Way. In 2 billion years, it'll start being a much more spectacular object for observation. In 3.7 billion years, it'll start to occupy our complete field of view. In 3.85 billion years, it will be ablaze with star formation because the gases in Andromeda will be colliding with gases in the Milky Way, causing the formation of stars, dramatically so. The star formation will continue at 3.9 billion years. Eventually, at 4 billion years, M31 will be tidally shredded and the Milky Way totally warped by the interaction. At 5 billion years, the cores will be two bright lobes starting to rebound, as you saw in the video. And at 7 billion years, we will have the core of an elliptical galaxy in our field of view. Amazingly, this collision involves more than 1.5 trillion stars, and yet it's not thought that any stars will actually collide. The universe is mostly empty space, so it's not likely to happen. The result will be a galaxy not unlike this one, M86 in Virgo. No spiral arms, spherical, or perhaps shaped like a rugby ball. It's also thought that maybe the Milky Way and Andromeda had a close passage some time ago, perhaps 10 billion years ago. That the Milky Way and Andromeda passed very close to each other, and Andromeda may have stolen some of our companion galaxies at that time. And now Andromeda is looping back toward us. Hard to know if this is true, but this research seems to indicate that this is a possible past path that Andromeda and the Milky Way have taken with each other. The halos of the two galaxies, by the way, are already colliding. We're down here where the Hubble Space Telescope is in the lower right. As you can see, the Andromeda galaxy has a halo that's been detected to an extent of over 1 million light years from Andromeda, and we're only 2.5 million light years apart. So the halos may already be intersecting. And so that's it. This is a galaxy that gave us an end to provincial bias that said the Milky Way is the only island universe, that the universe is static and is everlasting in the past and future. It taught us that there are countless other island universes, perhaps as many as 2 trillion within the observable part of the universe, that the universe is expanding and dynamic. It had a beginning and even has galaxies colliding with each other. It's a neighbor in space, and someone there may be looking back at us and saying, hey, we'll get together soon. So Scott and Terry and all, thank you very much for having me, and really appreciate the opportunity to be here with you tonight.
Thank you, Chuck. We really appreciate the fact you are here. You know, that's interesting. I always thought that when the galaxies would collide, that stars would be hitting stars. I never really thought about how much distance in space. I never thought about that. That's pretty amazing. And, you know, to be able to look up at some point, if we were still here, at that big galaxy, you know, in one of the stages it's in, can you imagine what that would be like for night photographers? We would be having a blast.
It would be something to see. No
It
question.
would. Definitely. Scott, you got any questions or anything there?
Well, I just want to thank our global audience here. We've got people watching from around the world. Some of them are old friends here. We've got Don Nab, Astronomical League's Don Nab, who's been on Global Star Party more than once. We got Andrew Corkill, who is Astronomical League member, and very active, observing program aficionado here. Fender 90 is watching on YouTube. We've got Helen Mahoney. Helen, I remember very well from the Riverside Telescope Makers Conference. And so she says it's always lovely to hear David read poetry. Andrew comments, he says, Corona Borealis has been getting fainter over the past couple of weeks. If it hits a dip and then goes even fainter, then get ready for it to pop. Chris Larson is watching on YouTube. He says hello to me and Andrew. Senthil Nagapan, whose son, Naveen, was on the Global Star Party last time. So he says howdy to everybody. Chris Larson, who else? We got Hippie Chick 57 watching from Southern Indiana. So hello, howdy to Hippie Chick here. We've got Beatrice Hines. Beatrice is in Belgium. And she says, howdy, star people. Happy Friday for me. It's Saturday. So I like our salutation of howdy. That is, I guess it's the official salutation of astronomers all over the world. So thank you for watching. And Mike Peoples is also watching. Mike will be at the Northeast Astronomy Imaging Conference and also at NEAF. He is a longtime astrophotographer, and so it's nice to see everyone there. And it was great to have you bring on Chuck Allen. I love his presentations, and he should make a collection of them to appear on the Astronomical League's website, because they are so informative, and so inspiring in the way that he presents them.
Definitely.
That's all I have, and perhaps you want to close it up at this point.
Yeah. I just want to say it is really nice to hear all of those names, because so many people there I know their names. Very few do I know their faces, but I know their name. I haven't seen Mike Peoples in so long. And Beatrice, Andrew, I mean, everybody here Don, we all know. But it is so nice to know that they're there, and we are sure glad you are there. I am going to make a couple announcements. We will not be back in April because most of us are going to be traveling. We got an eclipse to go to. We're going to be running around. So there will not be any AL Live in April. We will be back on March, May 3rd. So we will be back on May 3rd then. And I just wanted to tell everybody, just enjoy the eclipse. I hope everybody sees it that possibly can. I hope we all have clear skies. It is such an amazing event. If you've never seen it, you really want to see this, because you won't believe your eyes. It's beautiful.
Right.
It'll be my exoligmos.
There we go, Chuck.
That's a term that means solar eclipses that are separated by 3 18-year Saros cycles. Because I saw that one in 1970, and this is 3 cycles later. So I hope I get to see it.
Yeah, I hope everybody does. I mean, it is such an incredible thing to see that you'll just never forget it. So it'll be fantastic, I'm sure.
90% is good, but totality is the next step.
Yeah, 99.99 is not totality. Everybody,
it's not totality.
No, you need to be there. You need to be in the moon shadow.
The greatest expression I've heard is that the difference between 99% and 100% is 100%. And that's true.
That's good.
For eclipses,
I wonder if it's possible to actually be right on the edge of the center line, to where you could walk back and forth and see it not eclipsed and then total eclipsed, So
leave it to you, Scott.
You can do it in 4 minutes. I don't know.
You'll do it in 4 minutes.
The length of the eclipse.
Yeah.
Not that I want to give up any totality time.
Right.
Yeah.
Yeah.
But that would be amazing, wouldn't it?
It would be fun to do. Yeah.
Yeah, really.
You might
my
need
gosh.
an aircraft to do that or something.
Yeah, that would be good too. So
Right.
that is really all I wanted to say. Except thank you all for being there. Thank you, Carol and Chuck and Scott. As always, you guys
Thank
are
you.
great. I appreciate your support
Thank
and
you.
being there. And thank you to the audience. We wouldn't be here if it wasn't for you. So thank
Yep.
you so much for being there. And we will catch you on May 3rd. And Scott,
Yeah.
I'll turn it back
We
over to
should
you.
also mention that the Astronomical League, if you guys are fans of the Astronomical League, you should meet them in person at the Northeast Astronomy Forum. You guys will be there. And
Yep,
we'll be there
Carol.
too.
Yep, Carol, Chuck, and I will be at Neath. So
Yep.
I look
And,
forward to that. That is
Oh, it's a
such
fun time.
an amazing place
Yep.
yeah,
to
and
be.
David Levy's a featured speaker there. So,
So all 5 of us are going to be there.
that's right. That's right. So it's
Yeah,
going to be a lot of fun.
So come
it
see
will
us.
be. Yeah, definitely do that. It'll be great to meet people and put the faces with the names.
Yep.
So stop by the league booth, and Scott,
Oh,
thank you again. I will let you close it out.
okay. Thanks very much. Well, as our great friend Jack Horkheimer always used to say, keep looking up. Jack is also was a longtime contributor to the Astronomical League's observing or awards programs for youth, and so I like to mention him because he was such an inspiration for so many years. So, anyways, you guys have a great weekend, and we will see you next time. Take care.
Right.
Take care.